It's so loud. Okay. So let's get started with the agenda for today's tutorial. So this will be the last tutorial because the next tutorial we won't have much to discuss. So today we will discuss assignment number 3 solution. Okay. And then we will look towards evaluation metrics. Okay. And then probably we will take some break. And then we will go towards SCM, some theoretical exercise, right? And number 4, Q&A, if you have any regarding the whole course itself. Okay. We will also have, as already announced in the lecture, that the next lecture there won't be any more content, maybe just a little bit, but it would be primarily uh, dedicated towards answering your questions if you have any regarding the content of the course. Okay, so please be prepared, prepare your questions beforehand for the last lecture on Monday. And yeah, so most probably there won't be any tutorial happening because we would already be covering the question answer session in the lecture. Okay, yeah, so with this agenda let's get started. So I will be showing you guys some one particular solution for assignment number 3 so that you guys can. Okay, so just 1 second, maybe I open the PDF assignment. Okay. Okay, so the task, there was only one task in this assignment, so let's just quickly go through it. So on Moodle, you will find a Jupyter notebook, blah, blah, blah. So that contains a function for dimensional reduction via PCA. The function linear PCA expects that, 1 second. So the function linear PCA expects a data matrix of dimension P cross N and a number of principal components K. Okay. And then it returns the first K principal component analysis course for the matrix X. So subtask 1 was provide a code that tests the function with selected images from the provided MNIST training dataset by visualizing the first 2 scores in a scatter plot. Okay, and then we had to finish the gram metrics. Okay, sorry, gram PCA function. Okay, and then we had to test for implementation using gram PCA and linear PCA because if we choose X transpose X, then it is a linear kernel, so their output should be the same. So it is kind of a sanity check, right, of what's happening. And then we say that there's an unknown vector space H, blah, blah, blah. such that blah blah blah. Okay, with this Gaussian kernel, right? And then you had to choose this sigma by some manipulation, right? And yeah, so that was pretty much it. Okay, so now let's just quickly go through the solution. So this is the linear PCA function which we provided. Okay, and then we say part A. So, so we import some image input output libraries as already well known till now to you guys, and then we input some matplot libraries for beautiful plotting. Okay, so and then uh, we define some variables regarding the number of classes. Okay, so then we sample colors from a spectrum to represent each class. Okay, so this is again from this matplot library for representing the colors. Okay, it's just fancy stuff. Okay, so then we find the number of samples in each class, and yeah, so these are the variables. There, n is the total number of samples, x is data matrix, y is the label, c has the colors. Okay, and then what we do is that we read the data and we populate all these three matrices x, y, and c. Okay, this is pretty common. I think we have already done that quite a lot in this lecture already. Okay, so then what we do is that we first get two principal components from this linear PCA, right? And then we just randomize the order of the data for plotting so that one class is not entirely covered by another. Okay, so that's the rationale behind it. So then we have IDs, and then we randomly shuffle them, and then we have principal component of digit 0 and then digit 1, right? And then when we plot the first two principal components using linear PCA, so it looks like something like this. Okay, so the first two principal components, as you can see, that there's not much uh, information there, except that you see that all the colors are, or all the digits are on top of each other, more or less, right? Okay, great. I mean, not so great, but still great. Okay, now we're coming to part B, whether we complete this gram PCA function, right? And here what we do is that we again use this equation for the centering the gram matrix, right? Again, like I said, this is just one way of doing it. You could do it in many other ways, and I have seen some implementation by you guys which are also pretty cool. Yeah, so yeah, overall many of you got this assignment number 3 right, with little bit mistakes, but overall everybody was fine. Okay, so yeah, where were we? So then we find this using this linear algebra library, which simply get with SVD, and then we have the sigma, and then we using this sigma we get uh, the score vector S, right? And it is returning this matrix S. Okay, and here S, as discussed earlier, we have this K, right? So we only return the K elements. Okay, it appears only here. Other than that, it doesn't play much role. Okay, so now for testing the implementation, you just plug all these pieces together, right? And then what we do? Okay, 83%, right? Okay, and then what we do is that we have this gram matrix, okay, K, X transpose X, and then we calculate the gram PCA, okay, just for your reference. So this is a gram matrix, right? X transpose X, and again we simply are doing the linear PCA gramming, okay. And then again we calculate the same PC1 gram blah blah blah, and then we try to plot them. So basically if you see this, so this one is almost equally the same distribution, right, which was followed above here. Okay, so here we have try to keep the same color coding so that you could see that more or less the trend is the same. But if you have like if you have shuffled the data, then maybe the digits would appear a bit different. But overall, it should follow the same trend, right? That everything is mixed up with each other, with zeros being here, right, and with one and zero being mostly separate, because at least this much information is captured by this linear PCA, right? So it doesn't confuse zero with ones that much. But overall, the eights and nines are on top of each other. Okay, so the seven is also like all over the place, right? So there's not pretty much any information which is discernible by human eye, more or less, which is captured by this first two principal components of PCA, right? Okay, now we introduce this magic Gaussian kernel, and let's see how does this help us. Okay, so I think there was some instructions for you to follow through for the faster vectorized implementation, right? So let's just not focus on that too much. Okay, so okay, so what we do is that now we simply find out the pairwise differences of all the data, right? And then we take the squared norm for each of them, right? And then we plug each squared norm into the Gaussian kernel itself. So Gaussian kernel is pretty straightforward. Okay, let's just go through it again. So it is just this function: exponent x plus y whole squared, the L2 norm, right? And then we have divided by 2 square, 2 sigma square. So sigma is the parameter which we try to tune, right? Okay, and here we have sigma, and the sigma could be input to this function, right? So we can uh, try different sigmas and find out which one fits our problem better. Okay, so great. So since k is symmetric, so we just use that property, and we just populated j comma I using this I comma j, right? So we do not calculate for each and every. So this is just a way of computing it in a faster manner and a straightforward manner. Okay, I hope this point is clear. You guys know that k is symmetric. Okay, since there are no questions and no message in the chat, I assume this is already known. Okay, good. So right, so now we have this function blah blah blah, compute Gaussian kernel metrics, and then we pass it through gram PCA. Okay, so no questions so far, right? Okay, then we test this Gaussian kernel with the MNIST data, and we choose sigma is equal to 1000. I think this was the instruction in the yeah in the task that choose 1000 sigma. Okay, again k is equal to 2, and then we have 1000, and we plug in these values, right? So now we are just plugging each and every piece which we already figured out earlier, right? So yeah, so then we try to plot the personal component 1 and 2, and we can see that it is trying at least that, which I told you, that like that 0 and 1 are at least more and more separable visually here, right? So it is trying to take ones, because ones are like uh, quite distinct from zero if you see it from in the first impression, right? But again, this still is not sufficient, the first two principal components, but it is still better uh, than the linear case, right? Yeah, so that's it. Any questions, any comments? Okay, So since in this assignment there could be a lot of possible explanations, and since it was not like very I mean, it was very insightful to see it, to do it, but it was not very insightful to have a very concrete interpretation of these of this underlying phenomena happening. So that's why we did not ask any concrete things for you guys to interpret there, right? But I hope that you guys got the feeling of it, right? Yeah. So that's pretty much it from the assignment discussion. Okay. So now we move to the second task. So any questions? I'm just waiting here for 1 2 minutes. So if you guys have any question. So no question so far. That's okay. We can start talking about the evaluation metrics. So evaluation metrics. If any one of you know anything about evaluation metric, kindly unmute yourself and tell me about it, or yeah, the rest of the class. That would be pretty helpful, so that I know what you guys already know, and we start from there. Anyone? Any volunteer? No volunteer. Nobody's volunteering. You guys can unmute yourself, right? I think I have given permission for that. Yes, allow participants to unmute themselves. Interesting. Okay, so then I will assume and start right away. So, so evaluation metrics in machine learning are tied to some machine learning task. I mean, this is really important point. So maybe not just number them. I will just try to have some bullet points here, right? So the bullet point number one is, so they are tied to some machine learning task. So there are some evaluation methods which are general enough and they can be applied to many different tasks. But generally, if you have a very specialized task, then you want a very concrete evaluation metric to judge your model, right? So, I mean, in other words, uh, they are used to evaluate, right, as the word says, or measure the performance of a model, ML model, right? Good, cool. Okay, so yeah, that's pretty much it. So I mean, I will just refer here some tasks. Most of them we have already you might already be familiar with. We did not discuss much of them in the class, but I think you should be able to at least know the basics. So classification, as we know, like if we have a cat versus dog example, right? That would be, or spam versus not spam, right? So that would be a classification task, right? And maybe if you want like MNIST digits, classification, right? So that would also be a classification task. So I mean, it is mostly super. I mean, we have like supervisory labels available for this task, right? Labels are available. So, I mean, it means that you have the ground truth available, right? And then we have the regression problem, which we discussed, I think, a little bit also in the class. I mean, in classification, you have categories or classes. So you want to classify your data into like finite or countable classes. Okay. So, for example, MNIST has 10 classes, right? So digit 0 to 9. Okay. Similarly, if you have like spam and also there are two classes. So in regression, if we are actually the output of the model is not regarding the probabilities regarding some or decisions regarding some uh, what you can say regarding some classes, but or some group of data is not discrete in that sense, but it is continuous, that your output of the model is continuous. For example, in the case of stock market prices, right, or stock prices, we should call it stock prices prediction, right? So that kind of thing, because like a continuous number. Okay. And then another example could be that okay, so another example could be, for example, the problem we discussed, the housing price problem, right? House price prediction. So like the number is the continuous range, the output is continuous range. Okay. I mean, I'm just quickly glancing through them, not formally defining them. So at least you should have basic familiarity with this. So again, then we have the ranking problem, which is quite interesting in practice, because what I mean, for example, if you want to use Google search, then you type anything, then it is probably, I mean, there are many things happening in the background, but you could always think of the when you have all the results gathered, then how do you want to show them? Then that would be the ranking problem, right? So, so how to order the results in a good way, right? In response to a search query, to a query. Okay. Yeah. So that is the ranking problem. Okay. I think it is pretty much clear with the Google example. Everybody knows that. So yeah. So then we have clustering. Ranking is also a supervised problem, right? More or less, it's always supervised because we have some measure of defining the good. Okay. Maybe it is automatically annotated, or we have the automatic ground truth available, or in some cases we have the manual ground truth also available. So but clustering is an unsupervised problem. So we don't have any ground truth, and like we discussed, this PCA is an unsupervised technique. Always remember, PCA is an unsupervised technique. It may be that PCA, I mean, you do PCA, then you apply some logistic regression afterwards, or you apply some classification model afterwards, after reducing the dimensionality of the data. But still, it would be the PCA itself would always be unsupervised, because it does not require any supervisory label to calculate the principal component and components of the matrix. Okay. Yeah. Always keep this in mind. So clustering is really, really interesting. For example, if you have MNIST data set, then we could also try to figure out how the data is distributed underlying and what are the clusters of data. So we would expect that in practice that we have discovered more or less 9 or 10 clusters in the MNIST data set, right? Something like this, where each cluster belongs to uh, a single digit. Okay. So this is just for illustration purposes. I mean, we would expect the zero is here and one is here, right? This we don't have that label information. That's why I have colored them same because we don't have any way of finding whether it could be right. And then we have maybe 7 here and 4 here and 3 here and 5 here. Okay. So if we have something like this, then we say that okay, we have um, a very well separated data and a very well separation in the data distribution, or the cluster algorithm has performed quite well. Okay, but again, this is these all these things are like very general and very hand wavy kind of explanation to these models or these tasks, machine learning tasks. So because before going into discussing the evaluation metrics, I thought it's good that you guys at least know some of it. Okay, so cool. Now what we should do, maybe we take 5 minutes break. We join back at 10:10, 10:20, right? And then, yeah, so let's take 5 minutes break. Okay, so welcome back from the break. Today we were discussing this, yeah, this guy evaluation metric, but some one student told me about confusion matrix. So I think you guys are familiar with the confusion matrix. I will assume that, and it would take some burden off me because we have less time and a lot of things to cover for the evaluation matrix. So it's good that you guys, at least some of you guys, know about the confusion matrix. Okay, so yeah, so I would just say that, I mean, before, I think in the can you guys hear me? I mean, this is really, yeah, thanks, you guys can hear me because it's very odd to to keep speaking to a screen. Okay, so where was I? Yeah, so I mean, we have only covered one thing in the lecture, or up till now, one evaluation metric, which is called accuracy. It is a very very basic evaluation metric, like too basic, I would say, but it's also quite easy to understand. So I would just, why not just formally define it? You know, so you could say that number of correct predictions. Okay, I'm using shorthand. Pred means predictions. Okay, divided by total number of data points, right? So for example, if we had 1000 spam emails, so for example, just an example. Okay, it's quite simple. I think I should not even give an example. Okay, so because we will run short of time. Second is the confusion matrix, which some of you already told that you know. It's quite straightforward. So let's just also cross it, and then we have some AUC, but AUC would in itself, I'm just mentioning the name, so it's area under the curve. But I don't want to go into detail of this metric because it's very very useful. I really like this one in practice. Really useful, really awesome. But it's very cumbersome to calculate it. Okay, cumbersome metric. So I'm not going to discuss that in detail. But the idea is, you see the idea, if you're familiar with the confusion matrix, then these are two ideas are related. So that's why I'm not going to discuss them, because if you understand the confusion matrix, then you also understand the area under the curve, or AUC matrix, right? So I mean, it's actually not a single number, but it's actually a whole curve. Okay, so I will just maybe probably try to define it in the form of false positive rate. Okay, okay, false. Hmm. Okay, so maybe now you guys can read it. So this is false positive rate, and it is the true positive rate. Okay, so it is a curve between that. So normally, if you are randomly guessing things, then you are already on this line, on this red line, right? And if your algorithm or your model is smart, that it should be above this curve. You should have something, a curve like this. Okay, if this is one and this is one, right? Or maybe a curve like this, right? Something like that. So these would be the good models, because if your model is actually below this curve, like this one, then you can simply invert the prediction of your model, and you could get a better AUC curve, right? So below this red curve doesn't make any sense. Uh, yeah, I'm just going to leave it. Okay. Let's just go ahead. So AUC and mm, Config metrics are quite related. So now I'm going to talk about the ranking matrices. Metrics, right? So even before the ranking metrics, let's first discuss this precision and recall, right? Because these are also precision recall are also quite important ones, and they're also related in some sense to to the confusion matrix, and also um, they are both also very uh, popular in classification, right? So these are really interesting ones, and you would if you do any project in machine learning, you will uh, encounter them one way or the other. Okay, but I just want to give you a rough example of what's happening in the precision and recall, so that okay, so let's just use our colors smartly. Okay, so let's just see that we have a ranker and we want to evaluate how good our ranker is doing. Okay, so let's just say that we have this green circle. Okay, and it is all the relevant documents or the good documents which we wanted. Okay, so this could be, I mean, if you're thinking in terms of classification, this could be the spam email, right, which we wanted to get rid of. Okay, and if you think in terms of I mean, you have to define relevant again. So let's just consider the example of a Google search page, and if we have some good results which we know, which should form, which should be on the first page of the Google because they're relevant to the query. Let's say if somebody is typing Wikipedia and let's say TUM, then at the top, some pages TUM and Wikipedia pages should be in the top 10 results at least, right? So that forms basically a set of relevant documents or relevant answers. Okay, I just want to keep it general so that you could also think in terms of classification ranker at the same time. Okay, and now you have a ranker, and what this ranker is doing, this blue curve, okay, relevant items, I would call them items. Okay, and this is the returned items. Okay, returned by the ranker, right? By the ranker or classifier. I mean, our classifier thinks that these documents are good ones, so they will inevitably an overlap, right? This yellow area, and we are happy if this yellow area is big enough. We are, I mean, the more happy we are. Okay, so let's just call it, yeah, let us call this yellow guy happy items, or we're quite happy about them. Happy correct items, right? So, and then with this picture in mind, now I want to define uh, the definition or the mathematical definition of precision and recall. So just please keep this diagram in mind. Okay. Okay, maybe I will remove these guys so that I also define them over here. Uh, okay, yeah, that's better. Okay, so the precision of a machine learning model can be defined as, I'm using the color coding so that you guys can have could relate to this diagram. Happy correct answers or items, right? Divided by total number of items returned by the ranker. Okay, cool. And then let's just define recall. So recall would be defined as, again, these awesome, happy, correct answers. We are really happy about them because this is what we wanted to achieve in this whole model training, blah blah stuff. Ah, so where were we? Yeah. So do we divide now? What we divide with? So the numerator is same in both cases, but what we divide with is different. So number of relevant items. So I hope you guys understand this quite well. If there are any answers regarding this precision diagram, then please let me know. Because this precision recall is one thing which you would always encounter, or you should at least know about if you're doing ranking or classification task. So I mean, in other words, you could say that the precision is answering this question. Every evaluation is metric is answering some sort of question, okay, regarding the model. So, for example, precision is answering this question that out of the items that our classifier thinks are relevant, how many are actually relevant? You know, so this is what is measuring, okay, and the recall is asking this question from a different perspective. The recall is asking, out of all the items that are truly relevant, how many are found by our ranker? You know, so that's what we're doing. We're dividing by truly relevant items in the numerator in recall. Okay. So guys, any thumbs up or any yes to let me know that you guys understood this concept well? Moritz,
Hi,
please.
hi, Umar.
Yeah, yeah.
Um, I might have a stupid question, but so the set of the relevant items and the returned items, are they in the same magnitude? Because, for example, I have 1,000 relevant items, and I only want to return 10. Then my precision might be very high, and my recall can never be high, right?
Yeah, that's right. So that's why we always use these two metrics at the same time. You know, because what I could
Okay.
do that I mean, one very silly way of doing it would be that if I return all the items, right? I say everything is relevant. Then I have a
Yeah.
precision of 100%, right?
Yeah. Hmm.
But then my recall would be quite bad because do you
Oh,
understand the
wait, the
point?
other way around.
Sorry, what?
It would be the other way around, no? Wouldn't it be? Because I return all relevant items, but I return even more items. So my precision would be low,
Oh
but my
yeah, so
recall.
sorry, exactly. My recall would be high, but my precision would be quite low in that
Hmm.
sense. Yeah, yeah, yeah. Exactly,
Okay.
exactly. Yeah, yeah. Sorry. That would be the other way around. You're right. So that's why we want. And similarly, if I say that okay, um, I predict only one item about which I'm pretty sure it is right. Okay,
Hmm.
and like I don't say anything about the other items. Okay, so
Hmm.
in that way, the number of items run by the ranker would be like one.
Yeah.
Okay, or like very low. If I shrink that set, then my number of happy correct answer, if they overlap well enough, then my precision would be quite high, but my recall would be quite low because I'm not trying to predict all the relevant items. I'm just trying to predict only the most relevant, which I think the model thinks. because at the end of the day, it's
Okay.
probabilities,
Mhm,
and you are doing thresholding, right? Remember that question, yeah.
mhm.
So that's why I'm saying that you have to keep in mind what the evaluation metric is actually asking the model. You know,
Yeah.
every evaluation metric is a question. Think of it in this sense. So again, so the precision is that how many items that are classified by my model to be relevant are truly relevant. And
Mhm.
recall is asking the converse question: out of all the items that are truly relevant, how many are found by the ranker, right?
Okay.
Yeah, yeah.
So
Okay,
for
so
testing,
yeah, just one more. For example, this is in terms of classification. So, for example, if you are talking in terms of ranking, normally we do another thing. We say, okay, we are interested uh, only in top K items, right? Because Google doesn't want to know the whole set of documents, because that set could be quite huge, right?
yeah.
So they don't want to go into the millions of results. So they say, okay, we want to have top K items, and we would measure or think only based on top K. I mean, this K could be, I don't know, 5 if you are thinking in terms of Netflix, right, or
Mhm,
Amazon recommendations. They're 5, right, or 10, right, or
mhm.
20. So this is the normal. And if you are like abnormally, if your system is abnormally uh,
Yeah.
what you can say, the query is quite sparse, then probably you would go to 100, right? So it would be
Mhm.
normally in mostly in this range. From your own
Okay.
experience, you could figure it out. So okay, then what would we do is that we have actually applied a natural uh, boundary or limitation on the set on the returned items by the classifier. So this basically, this blue set would only be of K items, the top K items, right?
Mhm. Yeah.
Yeah, yeah. So there are many things which happen in practice, you know, and then
Mm.
we yeah. So then, for example, you have this again relevant items, and then you have might have some overlap between them. And there's another dimension to this question. So for example, I mean, when we are measuring in any test, we have several queries. We don't have a single query, right? So we might have
Mhm.
1,000 queries, and we are testing how on average our model is performing, right? And
Yeah.
then
Mhm.
we calculate, maybe at some points our model is perfect, and at some cases the model is like returning garbage, right? So there's no, I mean,
Mhm.
it could be that there is no overlap between those two sets, right, for some queries.
Yeah. Mhm.
Yeah, yeah. So then we just take the average over all the queries, and we live with that. But sometimes you say that, okay, I'm not interested in a model which performs very well on average, but is completely clueless on some queries. I want something which works almost all the time, right? Or I want an
Mhm.
example of that. That you do when you like according to your problem. So maybe you do in sampling of the models. You choose a
Okay.
set like 2 or 3 or 5 models instead of only one.
Ah, okay. Mhm.
So I mean, this is all what's happening in practice. Yeah, yeah.
Okay. Thank you.
Ah, you're welcome. You're welcome. So okay, another way, very interesting question uh, asked by you. So there's another actually a score which we call F1 score, right? It is quite popular in machine learning. And what this score is doing what you are trying to say, right? Try to find, give me a single number. I don't want to look at precision and recall. Give me a single number. This is what this F1 score is trying to say. And it is 2. It is actually the harmonic mean. So 2 into precision multiplied by the recall divided by precision plus recall. Okay. So now with this single number, you would
Ah, mhm.
get what kind of model you have, right?
Yeah.
Yeah. So I mean, we are using the harmonic mean here, like harmonic mean, and you know what the very nice property of the harmonic mean. So harmonic, like the arithmetic mean is okay. I would probably write it. So the arithmetic mean is biased towards the bigger of the two elements, right?
Mhm.
I mean, you could show it mathematically. So, but the harmonic mean, it is biased towards the smaller element.
Ah, okay. Mhm.
So that's why we're interested in the harmonic mean. Yeah, yeah. Okay, this is just one of the reason we use harmonic mean for this F1 score. Okay, cool.
Mhm. Cool.
So yeah, now we go to some other metrics. Let's see. There's a very, I mean, this is one of my uh, quite favorite matrices, but I think we might run short of time. Maybe just let's just cover this metric, right? Because it is really good. So it this is NDCG, and it is actually normalized, discounted, cumulative gain. Okay. Okay. So the reason for this metric is very uh, useful for the purpose of ranking. Okay, because the point was, uh, if you go back and see these guys, so there's no though there's no what you can say instrument, or there's no intuition that how good is the list of results returned by the ranker, because it is not measuring that. There's no, the evaluation metric is completely unaware of what you can say how the list is returned, and there's no position information encoded in the in the precision. Even if you have precision at top 5, then still you don't know uh, the position information is not encoded well. So I will just give it with an example. So let's just say that you have two models. Model number one, and it gives you a list of something like this, like 1 0 1 0 0 0. Okay, so we have like, okay, yeah, maybe just make it 5, and then you have model number two, and it is returning you 1 1 0 0 0. Okay, so I mean intuitively we would say that this, I mean, from the precision recall point of view, these are the same, right? Because they are both running two elements in the top 5, right? But the positioning is very important for the ranking algorithms, right? So here we should have some notion of quantifying this information. Okay, and this is just one e- example. Just I would just try to make it more extreme, right? So let's say you have two zeros here and two zeros here, right? And if you have a model number three, okay, so now we know that this model and these models, so this one is the best one, right? Because we don't want our relevant items to be on the position number 3 or 4. Okay, so these are the positions. But for precision and recall, they would be the same. Do you get the intuition? I hope so. So okay, so now we have the concept of cumulative gain. Okay, so the cumulative gain is that, okay, let's just take this example. So the cumulative gain is that I add how many elements I get, right? And then I just sum them up with respect to their positions. Okay. So do you get this point or not?
Yes, for
Yeah.
me it makes sense.
Yeah. So I will just try to write it in a mathematical form so that, yeah. So let's say the cumulative gain for a list of p items, let's say, is that I,
Amar,
yeah,
someone wrote in the chat that you might have to elaborate more on the ranking and what you said
yeah, yeah.
before.
So yeah, so I am just explaining that the ranking problem itself. Okay.
I'm not sure, but I think someone wrote in the chat, no, could you explain it
Yeah,
again?
yeah. Okay. So okay. No, I'm explaining it again from the with an example, right? So examples make sense. So cumulative gain is that you sum up the number of relevant items, okay, and which are at the position I, right? And then you also want to discount them. This is just counting. There's no position information here right now, okay? Then what we want to do, we want to discount it with respect to the position it appears, okay? I mean, you could do discounting in many ways, okay? One is this logarithmic way. I really like it, and this is pretty much uh, also prevalent. So what we do is that we divide it with the log of the position, okay? I is the position, right? So now we have this log discount there, right? I mean, you could also do it like this, or there's an alternative formulation, which is again you have I from 1 to p, and instead of relevance, you say that I want to have 2 into relevance minus 1 divided by I mean, so there are like many ways of writing it down, but the intuition is the same, that you want to discount. This is a discount of the position. So you have the position information in the metric itself, okay? So I mean, in other words, if you have the relevant items in the top position, that's this discount. I mean, the metric would be high. If you have the position, I mean, this I is relevant for higher I's, then the value of the gain would be very low. Okay, so just for example, in this case, for this position number 3, okay, so you would have let's say 1 over log of 3, okay, and here for this one also the same, but for this one you would have 1 over log of 2, okay, sorry, log of 1. Okay, if you are, I mean, again, this, sorry, this was the indexing problem. If you are indexing from I mean, if this is index number 1, then it would be log of uh, 3 plus 4, and this would be log of 2, okay. Okay, so let's just so this is the discount of the position, but then we also want that we have again I mean, this p is again the same as the k, that we want to be interested only in top 5 position or top 10 positions, right? So if we want to and the ndcg is simply that you have a dcg of a ranker, right, your ranker, and you want to divide it with the ideal dcg or whatever the ground truth is, right, based on that information. Okay, so that's it from the dcg side. uh, So now just quickly, I mean, there are other matrices, evaluation matrices, which are also quite cool. But yeah, I mean, for regression, we use this RMSE square matrix, root mean squared error, right, for regression. So which is like what was the ground truth divided by what was the prediction, and you just take the square of it and sum it and divide by n. Okay, and yeah, and then you take the square of it. So that would be for regression, right? So that's from the evaluation matrix side. Let's just uh, talk again about the exercise which we want to do today, the theoretical exercise. We still have 25 minutes to go. That's good. Are there any more questions? No. Okay, yeah, there's no more questions. So good. Now we are again going to the lab theory, right? So, so today we have a very interesting task again for the convex optimization problem, right? So the problem is that the optimal. Let's first write it down. It's actually a Troy problem, but since we don't have enough time, so we would not cover this SVM lab, which I discussed last time. But today with this theory exercise, I will try to explain you how this thing works from the with this Troy example. Then you could easily be able to understand the lab exercise. Okay, so we want to minimize x square plus 1 because I hope because here I will also discuss the dual problem, the pyramid dual problem thing, which was also the part of the lab. So with the straw example, I think it should be very clear. We would cover it in depth. So x minus 2, x minus 4 is less than equal to 0. So this is the optimization problem, right? So yeah, I mean it's quite simple. You could just simply probably calculate it by hand, you know, just in your mind also. So the first task would be what is a feasible set, you know? So what could be the feasible set for this problem? The feasible set is where the solutions could lie. So for that we just look at the condition on the optimization problem, right? Which is this. So we understand that from this that feasible set S should be from 2 to 4, right? So this is where our solution would lie. And what would be the optimal solution? If anything is not clear, please let me know, because I think it is pretty straightforward. I mean, I'm just writing by hand so that you already know the answer, and then you can easily um, follow what is what when we make it more complicated in terms of KKT conditions and Lagrangian function and dual problem, right? So, and the optimal value would be, because we want to minimize it, so then the minimum of this solution set would be the optimal value, right? So the x star is equal to 2, because we have the monotonicity of the solution there, because x cubed plus 1 is a monotonic function, right? I mean, you could write it like that due to monotonicity of the function, but it's pretty straightforward. Okay, so since the formally speaking, since it is a monotonic function, so the optimal value will be the leftmost or the smaller most value of the feasible set. Okay, and the optimal solution would be if you put this 2 into this equation, right? So that would be 2 squared plus 1, 5. So that would be the P star, the optimal solution would be 5. Yeah, so far so good. Okay, now I want to just complicate it, because we are trying to understand these KKT conditions, which are quite complicated. But with this exercise, I hope that you get the right equation, the right intuition. So the task B, which we have defined, is that rewrite it in terms of KKT conditions. Let's make it complicated. Life is not fun without complications. Okay, so we've write the Lagrangian function x lambda x square plus 1, and now we define the constraint minus lambda, and we add the constraint here. The constraint is x squared plus 6x minus 8. So this was the constraint, right, which I have written here. I have just opened it up and written it there. Okay, so far so good. If nobody interrupts me, then I'm going ahead. Okay, so now we write the KKT conditions. Why is minimum x square plus 1 subject to what?
Sorry, yeah, I have this question. Why is the x squared plus 1 subject to this other expression in the other slide? The last slide you wrote that. I didn't understand. It's exactly so, like the minimum of x squared plus 1 is subject to this other expression.
We have to minimize it, right? We have to minimize this guy.
Mm-hmm.
We have to minimize this function, and this function is subject to this condition. Okay, so let me just write it in another way so that probably you would understand it better. So we are minimizing, we want to minimize f of x, and f of x is subject to, let's say, g of x. Yeah, do you understand now or not?
Okay. Yeah. So like Moritz said, so it's the optimization target is f of x, and
These are the conditions,
it's the condition that we have to.
Yeah,
Okay.
exactly. Thanks.
Yeah.
Okay,
Thank you.
so now we write the KKT conditions. I mean, from the lecture notes we already know them. So I'm just going to assume that this is pretty straightforward for you guys, because we simply take from with respect to x, and you say that, I mean, we have, okay, I'm just writing down 2x plus 2 lambda x, then minus minus 6 6 lambda. Yeah. So this should be subjected to 0, right? So this is first condition, and the condition number 2 is that minus x minus 2 x minus 4 should be greater than or equal to 0. I've just added minus here because I just want to keep it the same as because it was like less than or equal to 0. I just want to keep it consistent with the lecture notes where we have greater than 0 notation, right? So that you guys can easily relate it. So this is one condition, and then we also have another condition, which is that lambdas, all the lambdas should also be greater than 0, right? And also we have this lambda into this constraints x minus 2, x minus 4. This should also be greater than or equal to 0. Sorry, this should be equal to 0. There's an equality there. Do you remember the KKT conditions from the lecture notes? So this is pretty much it. So we have that all the CI or the lambda stars should be greater than or equal to 0, let's say, and then we have the lambda into the constraints. The CI of Z star, I think that's what the lecture note says. So the inequality and the equality constraints, if you want to multiply them, then they should be 0, right? And the inequality constraints should be greater than or equal to 0, and the equality constraints should be equal to 0. That's what they are, like equality constraints. But we don't have any equality constraints here, right? In this example. Okay, cool. So this is done. This part we have written it down. Now we want to do a funny thing. We want to find out state this as a dual problem, right? Of this problem, and we then find the optimal value of this dual problem and the optimal solution of this dual problem. Okay. So how to do that? I mean, this is very easy in this case. Let me just say this loud so that everybody understands this. Because I mean, figuring out the dual problem is not easy in every case. But the reason why we go towards this dual problem is that sometimes when we state the dual problem, it is much easier to solve from the numerical point of view or from the algorithmic point of view. And the primary problem, that's why we have this idea of primary and dual problems. Uh, so I mean, in this case, both problems are toy problems, so they're both easy to solve. So this may not make much sense to you, but please understand the idea that why we want to go towards the dual problem sometimes, because it is very easy to solve numerically or from the algorithm point of view. Okay, yeah. So I mean, in this case, we know exactly the Lagrange function is a squared function, right? And its infimum can be easily determined by setting it to 0, right? So for example, this guy, okay, so when we take the derivative of it, it is this guy, 2x plus 2x 2 lambda x minus 6 lambda, right? If we set it to 0, then we easily find the infimum for this function. Okay, so I'm just again rewriting it for the sake of completion. Okay, okay, 6 lambda, this should be equal to 0, right? And then we you can easily solve this and find out that 3 lambda over 1 plus lambda, this should be the infimum value. Everybody understood this? Okay, so now for the Lagrangian dual function, what we do is that we say that the function is given by okay, the Lagrange dual function would be LD. I think this is a notation in the lecture notes, if I'm not mistaken. LD lambda. This should be the infimum over x, and lambda x lambda, and instead of x we put this guy 3 lambda over 1 plus lambda. I mean, that's the whole trick, right? And then you put this, I mean, this L is basically this guy. Okay, I'm not going to write it again so that yeah, so when you put that into this lambda into that function, so and when you try to solve it, you would find out that the expression simply resolves to 9 lambda over lambda plus 1. Okay, yeah. So now the dual problem is given by maximize, because we had the minimization there, so in the dual we would have the maximization, right? Maximize minus lambda plus 1 plus 9 lambda over lambda plus 1 subject to lambda in greater than or equal to 0, right? Everybody is with me? So now if when we differentiate it with respect to lambda, now it's a single variable, so we simply use d dld over d lambda right. You could use the chain rule and differentiate it, and yeah. So and we have this constraint that lambda is greater than or equal to 0, and if you put this, then this equation can only be solved with two in two ways, right? So there could be only two possible candidates. So one would be the lambda 1 is that this guy is 0, right? Or the second would be the lambda 2 is that this guy is 2. Okay, because if you have 0 here and if you have what you can say 2 here, then still this would be the only two possible solutions for this equation. Okay, so far so good. I hope I don't need to you guys can easily calculate this guy. I mean, you can easily solve this, hopefully. So again, also we see that this lambda 2 is greater than or equal to lambda d of 0, right? It's like simple. Okay, let's just calculate it. If you put lambda d is equal to 0, then we have 8, right? Oh no, no. We have to put it into the main function, into the Lagrange function. Sorry. So let's just put it minus 0 plus 1 plus 9 into 0 over 0 plus 1, right? And then we would have something like 9. Okay, and if we have lambda 2, and then we have minus 2 plus 1 plus 18 over 3, 6. So we have minus 1 plus 6. Okay, there are some questions in the chat. Minimum is your precision. Okay, no, these are the old questions.
Could you share your screen for a moment again? I can't see it right now.
Yeah, I was just looking at the chat, so
Oh, I see.
okay, so yeah, so there are no more questions in the chat. So basically, here we see that since the LD2 is greater than LD0, so we have lambda star is equal to 2, and then again if we put it there, so the lambda d star the solution would be also 5 in this specific case. Okay. So any other questions regarding this?
Why was the first solution 0? We calculated derivation, right? And then we set it to 0, and we try to find the solution. Is that correct?
Yeah. So yeah, exactly.
But when it before, could you go back to the page? Maybe?
No, man, that is lost.
Oh, okay.
Because
okay.
yeah, that is lost. So you have this minus lambda square plus. I'll just write it again. Yeah, I think it was something like this, right?
Yeah. Mm-hmm.
Okay. Yeah.
So why is lambda equal 0 a solution? Shouldn't it be lambda equal 4? Wait. Because I think we can factorize this the product the term above, and yeah. I think.
I mean, I don't want to go to show you. I believe that you guys can find it out because we have less time, and I want to go and discuss one more thing with you guys.
Okay. Yeah. Go ahead.
So I mean, when you figured it out, then you would see that the lambda star, the optimal solution in this case would be the 2. Okay, the
Yes.
possible the possible lambdas are 0 and 2, but the lambda star, the optimal is 2, right? And when you put that optimal lambda into the into lambda d lambda star, then you would have the answer 5,
Which is like the same as our primal problem.
which
Yeah.
was the same as the primal problem. So in this case, the strong duality holds.
Okay.
I mean, this is not always the case, but in this case, we can see that the strong duality holds. The dual solution the primal solution coincide. So so basically under certain conditions, which almost which occur in the case of STMs always, right? The minimum of the problem
Yeah.
also coincides with the maximum of the dual problem. Okay,
Mm-hmm.
so in that case, we say that the strong duality holds. Okay,
Okay.
yeah. So
Thanks.
going again. So now we just want to see that if we want to put this uh, the dual solution into the primal problem, and then we want to see what is happening over there, right? So let me just make it more concrete. So the D part is we are just now putting everything x lambda star instead of, so we are putting the optimal solution, the dual solution from the optimal solution from the dual value, right, in this equation. So 6x minus 12 is equal to 0. I mean, originally, okay, let me maybe write original so that you guys understand what's happening here. So originally it was 2 2x plus 2 lambda star x. I'm just writing star now, okay, minus 6 lambda, right? And when you solve this guy, so you would have 6x minus 12 is equal to 0. And then you simply would have again uh, lambda star is 2, right? So these are the original KKT condition in which we are putting these values, right? So the lambda star was greater than or equal to 0. So 2 is also greater than or equal to 0. So that condition is checked, right? And then we have, I mean, again from this you would also get x star is equal to 2, right? From that KKT condition also. And then again, if you remember that the way we multiply the inequality constraint with the equality constraints, that fourth condition, and if you solve this guy, then also the answer would be x star is equal to 2. I mean, this works because the strong duality hold, otherwise it would not work. I mean, the dual solution does not always lead to a unique point that fulfills the KKT conditions. But in this case, since the strong duality holds, when we put the optimal value lambda star into the KKT conditions, we have the same optimal solution x star, which is 2, right? Do you guys understand this point? Hello?
Yeah, I understood it.
Okay, just one. I mean, this might be a bit confusing because, yeah, strong duality doesn't mean that lambda star is equal to x star. I mean, this is not the case. Well, this is important because in this case, actually, the values are also the same. So some people may get confused. Doesn't imply strong duality. I mean, what does the strong duality implies that from strong duality, the solutions, the P star should be equal to the lambda Lagrangian of the lambda star, right? This is the condition of the dual problem, right? Okay. I hope you guys understood this one. So this is a strong duality, not this one. Yeah, that's it. Morris, do you understand that?
Yeah, thanks.
Yeah, so that's it. We are already 1 minute up from our time. So thank you guys for attending this course. And if you have any questions, please write them down, go through the lecture notes and the tutorials again, and ask them on Monday. Okay. Just for the purpose of completion, I would say that there will not be any programming exercise in the final exam. There will be some practice exercises in the sense that you would need a paper and pen. That's very important for for finding out the solutions, because if you want to do matrix multiplication, so you would need a paper and a pen, and maybe a calculator with you. So just keep that in mind when you get uh, when you sit down to solve the exam. Okay, and the exam would be online, as already uh, conveyed to you guys. Okay, so thanks, have a great weekend.